I'm here to talk about how virtualized network stack in FreeBSD can be applied for emulating large-scale networks. So here's the outline of my today's talk. So first of all, a brief background, why am I so obsessed with network emulation? So first of all, it's pure fun to be able to run hundreds of virtual routers on a single laptop, each being fully functional, running a routing protocol, traffic source or analyzer or something like this. Second, I'm employed at the university in Zagreb, so occasionally I'm forced to teach some basic networking courses. So in such cases, an emulator can come as a handy tool for showing various issues that one can experience in real networks to students without actually needing to have a physical lab environment. And finally, there are people out there who are really interested in using FreeBSD as a platform for research and development, for network emulation as validation tools in research and development. So basically, what are we going to talk about? We are going to talk about how we can construct virtual networks using virtual nodes, which in FreeBSD are constructed from jails with virtual network stack capability. We'll talk how those virtual nodes, which are isolated by definition, can be interconnected together in arbitrary topologies. And I'll talk a bit how netgraph, which is a standard framework in FreeBSD, can be used for that. And yeah, we are here because all of this is working in a virtualized FreeBSD kernel, not Linux. So at the beginning, just to position ourselves at the right place in the virtualization spectrum. So these days, everybody is talking about virtualization. Most of the people will start thinking about Xen, VMware, Oracle, VirtualBox, things like this, when they hear the virtualization buzzword. So the virtualization idea is not new, and it was pioneered, I think, maybe 40 years ago by IBM, and IBM still sells huge mainframes based on the capability that they can actually emulate hardware to expose an illusion of running operating system on a virtual hardware, while in fact the hardware is shared among several or maybe hundreds of isolated environments. So this is not what we are going to talk about today. Today we are going to talk about a different approach, which virtualizes a single OS operating system kernel and then provides mechanisms how to create an illusion for applications and users that they are running all by themselves on an operating system, isolated from perhaps different sets of such applications and users. FreeBSD jails, FreeBSD pioneered this approach, I think, with jails, but today we also have Solaris zones, and Linux has different approaches how to do something similar. So basically, this is the focus of today's talk. And obviously, those two approaches, virtualizing hardware and virtualizing operating systems, have different advantages and drawbacks. So virtualizing the entire hardware is really a heavyweight approach which provides perfect isolation between those environments, but as many of you might have tried, you cannot run more than 2, 3, 4 instances of VMware on a laptop, or perhaps more if this is a beefier machine, while if you virtualize an operating system kernel so that it provides only the necessary subset of what the isolated environments need to see, this approach can scale pretty much higher. But obviously, if the operating system kernel crashes or you get serious security exposure, well, then all the environments are likely to be affected. So the idea behind this talk is to combine the hands-on approach with a theory. So I'll take my chances, and before proceeding with any of my lamentation, I'll try to do a short demo to show you how using a simple GUI tool, we can really quickly instantiate a virtual network on a virtualized FreeBSD kernel, and then we'll discuss how this really works. So, well, wish me luck, and let's see. So basically, we have a simple tool written in tcl-tk that we can use to define a set of nodes, attempt to connect them, and say execute, and with a bit of luck, the laptop hasn't crashed, which is a good sign. We have a virtual network of 6 routers running on this pure laptop. So let's switch to this node, show IP route. So I'm running a Quagga inside a Quagga shell on the virtual node N0. And what you can see is that, well, the guy has learned all the routes from the other routers, and probably we can try to ping one of the peers. This seems to be working. If we start a shell, we'll see that we have a set of Quagga daemons running here. If we open a similar shell on another node, so we'll see another set of Quagga daemons, but well, looking by process IDs, you might notice that there are different processes. We might run a TCP dump. Here we are running on a virtual ATH0 network interface. We see some RIP traffic. If we do a trace route to that node, that would be ATH0 would be 10.0.2.2, 10.0.2.2. We'll see real packets flowing to this network. So basically, inside each of these nodes, we can run any FreeBSD application completely unmodified. The environment that we are running in is essentially the same as in the standard FreeBSD jail. The only exception is that instead of being bound to a single IP address, each jail has a fully independent instance of networking state. So if anyone has any questions, please feel free to interrupt me. Okay. So basically, I just wanted to get you a feeling what we are talking about. So So basically, what have we seen in this demo? So we saw that we can create, we created a small experiment with only 6 nodes, but each virtual node is really lightweight, so this can really scale to hundreds, if not more, virtual nodes on a single machine, depending really on what one wants to run in each node. So each node has its private routing tables, TCP, UDP port space, firewalls. We can even run Linux binaries, unmodified, in each virtual node. The packets that flow through the virtual network are not copied anywhere. So they are just moved by reference, a pointer to each packet, once the packet is in the kernel. We only, when forwarding a packet from one virtual node to another, we actually only forward a pointer to that packet. The packet is never copied or moved until it goes out to the user space or goes out on the physical network. So this really works fast. We saw that experiment can be instantiated quickly. We don't have to wait to reconfigure our network as we would have to do with VMware or Xen. And the best of all, the network stack virtualization technology has been merged into the main FreeBSD 3. It is still marked as an experimental feature, which really has a few known bugs, and I wasn't sure myself whether my laptop would explode now or not when doing this demo. But it's being really, really improved. There are several people seriously working behind this, and we had a lot of support from the FreeBSD Foundation and other entities outside of the FreeBSD community. So the hope is that this will become really mature soon enough. But if you wish, you can try it with FreeBSD 8.1. This should be in a pretty decent shape. So how does this work? The basic idea is to provide each virtualized environment with an independent state independent networking state. So we reuse the existing kernel code. We actually don't modify it. We extend it so that the variables that define and describe the network stack, which are normally residing in a global address space, that they are in some way compartmentalized so that they can exist in multiple instances. So that each of those virtual nodes can possess its own copy of networking structures, routing tables, all the necessary variables. We'll see later that this can be accomplished in different ways, but that's essentially the key. So the idea is extremely simple. Again, the idea is that just as in plain jails, user processes are always attached to a single network stack at a time, that all physical or virtual network interfaces must be always attached to a single network stack at a time. And as said, by definition, the network stacks are isolated. So if we want to connect them, then we have to do something. Questions? Okay. So basically, this is just a recapitulation of what I said. The basic concepts are that sockets, network interfaces, and user processes always stay attached with one network stack instance. So you cannot move an open socket to different stack or have a physical interface appearing just like that in many virtual stacks. Some bridging method must be used to accomplish that. So here's a brief history on how this technology evolved. FreeBSD jails originally appeared sometimes around 99, and jails basically provide the ability to group processes together, have them running in a change-routed environment, protect them from the processes running in parallel such groups. But from the networking perspective, they are just getting a little share of the networking view of the hosting system. So basically, they are bound to a single IP address, and all the routing, the firewalls that has to be configured for each of the jails from the outside, from the hosting environment. So later, the limitation of having a single IP address per jail has been alleviated, so these days it is possible to have multiple IP or even IPv6 addresses. But essentially, this approach is just subsetting of the whole view, whole networking view that the hosting environment has. So in 2002, well, just of pure curiosity, I did a proof of concept experiment. So I tried to whip off all the global variables that were relevant for the networking to a huge structure. Basically, the FreeBSD kernel is a huge C program, so we just place those in a huge C structure. And all the access to such virtualized variables was, well, to be honest, manually changed throughout the networking code so that each reference was prepended by a base point and dereference. So at each point where we accessed a networking variable, we were actually doing this via a base pointer. And what had to be done on top of that is that each function in the call graph, whether it was called from above from the socket layer or triggered by an incoming packet, had to know on which of those independent structures to operate on. So at the entry in the network stack, we had to set the correct pointer, and originally that pointer was passed from each function to another as an additional argument. The whole code churn was and still is confined below the socket layer and above the device drivers. So none of the network device drivers had to be modified, well, at least not those that had a clean design. There are a few of those that had some issues, but in 99% there were no changes at the device driver layer. And in this prototype, IPv4, IPv6, IPSEC, the whole transport layer, and IPFW firewall was successfully virtualized. The whole system worked reasonably stable, and most important of all, it was really, really fast. So that additional level of indirection proved to have almost no impact on performance whatever, at least in FreeBSD 4 days. These days we have a little bit more levels of indirection, so well, we'll talk about that later. So there were some anecdotal reports that some ISPs actually use this in production, but for several reasons this never made it into the main FreeBSD 3. First of all, the changes were really like just piled up to work, really intrusive, and couldn't be conditionally compiled out. But the biggest issue was that as all the global variables were put in a huge contiguous structure. Each time the layout of this structure would change. Any ABI contract with external KLD loadable modules would get broken, and things would no longer work. And of course, FreeBSD 4 was a dead branch around 2005, so this prototype more or less died slowly. Based by a push from ISC, the Dutch NLnet and FreeBSD Foundation decided to come forward and put some funding into trying to re-implement this from scratch, probably in a proper way this time. So at this point in time, this was no longer a one-man experiment, but the community, start to pick up on the project. So the new prototype was done from scratch in Perforce. It was continually kept in sync with FreeBSD current. It happened that we didn't make it in time for FreeBSD 7 for this to be merged, but this implementation managed to really accomplish that all the changes can be conditionally compiled in or compiled out. So if we do not define options of image when building our kernel, we get just a plain networking code as we had it before. It appeared that the need to pass an additional argument, a pointer to the Vnet context to work on, was actually not necessary if we could pass this implicitly as a thread local variable. And this seems to work well. So no function definitions had to be changed in the existing code. And an attempt was made to break the huge virtualization container into smaller, separated per module structures to reduce the impact of the changes in structure layout to kernel ABI. This worked, but it appeared that a better method, could be accomplished. And one more thing: at this stage, we successfully pioneered hierarchical organization of those virtual environments. I called them Vimages at that time, and these days the Vimages or virtual network stacks are pretty much integrated with jails. In 2008, it was decided that the prototype was reasonably safe to merge into the FreeBSD 3, and particularly Bjorn Zec got to great lengths to prove that the changes that we were merging in incrementally didn't change anything in the existing code, and that all the changes could be compiled out. Jamie Gritton implemented a new jail management interface, so now the network stacks hang off from jails, and jails can be arranged in a hierarchical manner. So we can have one level of jails that has several children and so on. Perhaps the most important change was done by Robert Watson. I think, many people were involved, and basically at this point in time, it really became a community effort. I was more or less hands-off at this point in time. So the problem of the ABI breakage, if any of the virtualization structures would change in their internal layout, or any of the structures that were embedded inside would change in layout, was really considered to be a huge showstopper. So based on how per CPU variables can be sorted by a linker to be in a contiguous address space. The same trick was used to force the linker to put up all the networking variables that are marked for virtualization in a contiguous address space. So that means that those variables are no longer scattered around or with, say, VM variables, TTY, and so on, but they're really in a contiguous space together with a bit of a buffer, which allows KLD loadable modules to be assigned a chunk of memory if the buffer is sufficiently big. So the idea is that if those variables are stored in a contiguous space, then this space can be, the layout of this space is defined at link time, and really there is no ABI issues, because the linker will sort the variables always in a proper way. And this contiguous space can then be allocated in multiple instances. And this also allows us to use the initial set of the variables as a read-only template, which can be used to initialize all the instances of the virtual network stack that get created at runtime. We can talk about that in more details if anyone is interested. So basically, 8.0 release was shipped as options image capable. So FreeBSD 8.1 release will contain many fixes, mostly done by Bjorn Zeb, who got some funding from the FreeBSD Foundation. And one of the most difficult issues to solve with the network stack instances that can be created and deleted at runtime is that our network stack was never designed to be cleanly shut down. So basically, we just, when we are rebooting, we just shut down the machines. We do not stop timers. We do not release memory. That was never thought of and planted into FreeBSD. So the destructors for all the virtual network stack instances had to be carefully implemented, and the most important ingredient was the framework for correct ordering of the invocation of constructors and the destructors. Still, many important subsystems are not virtualized, most notably PF and the related stuff. So the goal is to have production quality virtual network stack in FreeBSD by FreeBSD when 9.0 or 9.1 ships. I'm pondering about the idea to allow a single process to connect with multiple sockets in multiple network stacks, serving like an application level hub between those. And Bjorn is working on generalizing the virtualization framework to be applicable to different subsystems like System 5, IPC, perhaps CPU scheduling, who knows what comes next. Okay, that's basically it regarding the network stacks. So by definition, all those network stacks, as said, are isolated. So we need some way of providing network visibility, connectivity between those. So one way is to use specially crafted virtual Ethernet interfaces, which Bjorn implemented, which basically are always created in pairs. So we can have a pair of back-to-back connected Ethernet interfaces that one can assign to one virtual network stack, and then the packets can flow through it. In my experimentation with network emulation, I'm relying more on netgraph. So netgraph is a subsystem in FreeBSD that allows arbitrary manipulation of network traffic. This is mostly done on link layer, but there are many node types that can perform many different functions, and it really depends at which point one inserts something in the netgraph topology, and then what one wants to do with this. So netgraph nodes are processing elements which can be either internal, so they are, in which case they are only netgraph nodes, they have netgraph hooks and nothing else, or they can be edge nodes which allow for interaction between netgraph and, for instance, Ethernet subsystem to inject raw packets to UDP or TCP sockets. There's I think whole Bluetooth stuff in FreeBSD heavily relies on netgraph. Anyhow, this is a system which mostly by functional calls passes MBUFs, so network packets, from one processing node to another. So here's a list of a few most widely used netgraph nodes. ng-ether attaches to a physical or virtual Ethernet interface and makes it able that we intercept packets and that go from the network card to the upper layer of the network stack. We can intercept them and route them through an arbitrary setup of netgraph processing elements. Netgraph E-phase Ethernet interface is a virtual Ethernet interface which only has a netgraph hook on its bottom. So it has to be connected to a netgraph bridge or something like this to be useful. And so on and so on. So basically, based on interconnecting netgraph nodes in desired topology, we can construct arbitrary topology with netgraph and virtual network stack. So here's a possible scenario how netgraph nodes can be connected. So we can have an Ether node which might be attached to, say, our EM0 or BGE0 physical Ethernet interface. We can insert a bridging node between the upper and lower hook of this edge netgraph node, and then all the packets that come in from the network will be routed here. If this bridge is smart enough, then it can operate as a self-learning bridge and do the right thing to switch packets based on the destination MAC addresses. Or we can simply connect two virtual Ethernet interfaces back to back together, or insert a processing element in between. ng-pipe is a processing node which allows us to emulate bandwidth delay, bit error rate, packet duplication, impairments like those. So now we come back to what we saw in the demo. So basically, this is from what we saw in a GUI. We have three virtual network stack instances, three Vnet jails we have an netgraph, a pair of netgraph interfaces connected back to back, connecting those two Vnets together, and well, that's it. That's how the packets flowed in the demo that we saw. So, well, as said, I'm a bit of network topology emulation freak, but in this example, we can see how we can create Vnet jails, which might be used just for pure virtual hosting. Perhaps we want to have multiple virtual hosts. Each environment would probably then, in that case, have its own change-rooted environment. So we use the jail command to create the Vnet jails. Well, here's the syntax that you can see, and then in each of those jails gets its own independent loopback interface instance. We assign it an IP address and bring it up. Then using an ng control utility, we create netgraph nodes. We create two e-interface nodes, which we can see here and here. And if config ng-ath0 to Vnet n1 and if config ng-ath Vnet 1 to Vnet n2, we assign those interfaces to jail n1 and jail n2. And if we are going to really configure the topology as depicted here, it's a good idea to put the EM0 interface in promiscuous mode so that we could receive Ethernet packets for MAC addresses that will be configured on those virtual nodes. So in this step, we create a netgraph bridge. That's this object here, and connected with netgraph node EM0 to its upper hook. So this line creates netgraph bridge here and connects the link hook to upper hook of the EM0. The next line just gives this node a name, because by default the bridge node does not automatically assign itself a name. Here we connect the lower hook of the EM0 to a hook named link1 of the bridge node. So after the third line is executed, we have EM0 pushing all its traffic through the bridging node. And then we can connect ng-ath0 and ng-ath1 to the corresponding hooks of the bridging node. So we have assigned those interfaces to the jails N1 and N2, but they have still remained visible in our hosting environment as netgraph nodes. And basically, this is what we can see if we switch to execution in the context of the jail N1. We spawn a shell there, issuing if config. We can see that we have a loopback interface and a virtual interface ng-ath0, which doesn't have any MAC address set, so we have to, just for consistency with the picture, we name it, give it the name ath0, we give it a link address, we give it an IP address, and basically we should be able to get to the outset world. So that is basically what is going on under the hood of the GUI with dancing routers that you saw at the beginning. And basically this is a typical set of steps that one would go through, probably in a script, if one would want to set up virtual hosting environments with multiple Vnet jails. So basically that's it. If you want to try this out, just install FreeBSD 8.1 rc.2, rc2, or I think rc3 is not yet out. If you want to play with the network emulation GUI, you can fetch it here. A fork of this tool has been compiled by Boeing and has a netgraph node which allows for emulation of Wi-Fi networks. So you can you have a matrix of like a bridging node with many links, with many hooks that you can program which peer can talk to which one. So quite useful stuff for ad hoc network routing research. Bjorn has put a wiki page here where you can find some pointers about the current state and development of the virtual network stack in FreeBSD. And, well, feel free to ask questions on the mailing list where I do not answer all the time, I must be honest, or feel free to ping me directly. So basically that's all. If you want to discuss the technical details about anything, well, feel free to shoot. Okay.
Thank you very much. Any questions?
Hello. You mentioned that CARP and PF are not supported yet, I guess, because they are from OpenBSD import. How is it with VLANs? Are they completely, do they cooperate with virtual networking without problems?
To be honest, I haven't tried it out recently, but my guess is that the system would most probably panic if one would try to run with PF. PF is actually virtualizable. I managed to do it myself once, but then fresh import of newer release of PF came in, and then I just couldn't put aside another 2.5, 3 weeks of work to do that from scratch, because the import was, well, the code more or less completely changed. So the old effort couldn't be reused. But I'm not the right person to answer about the PF, but there is some work in progress, and it's most probably that this will be merged soon in FreeBSD current. So, for example, in FreeBSD 8, we don't have virtualized multicast routing, but this has been just merged to current. And, well, I expect slowly that the missing subsystems will get covered by the virtualization. But the problem is that as virtualization is not turned on by default in FreeBSD, sometimes developers just forget about that feature, and we get some changes. For example, something was changed in IPFW, and there was some leakage between the virtual network stack instances, and I don't know what exactly, but it took a while for Bjorn to bring it up to life. I'm not sure if in FreeBSD current it's okay these days. So it would be a good idea to attempt to push options image as a default in FreeBSD current to, well, bring those issues more to the surface.
Any other questions?
Hi, Marko. Maybe you can answer. There was talk about using virtual network stacks separately from jails. Is it possible to create a few virtual network stacks within one jail? and also to create multiple jails in one virtual network stack?
It is definitely possible to create multiple jails inside one virtual network stack. So we would create a jail which has a network stack, and we would then create an offspring, children of this jail, which each of which would be bound to an IP address. So we would obviously, for the top level jail with the network stack, we would have to configure multiple IP addresses, and that would work.
But those processes would be separated, just like in jails. But can we create few processes that can communicate with each other using, I don't know, Unix domain sockets, but still be assigned to different virtual network stacks?
I don't know the answer. I don't know the answer. That was something that I wanted to have, but I didn't write the new jail management interface. To be honest, I used the vimage command just until a few days, which is not something that's officially supported with jail. So.
Okay, and my second question is, if we have the image option compiled in, but we don't want to use virtual network stacks, we just want to create simple jail, set up simple jail, do we pay a price? What's the difference in overhead, in memory footprint, as compared to older jails?
So the only penalty that we pay is that actually the networking state is kept in two copies. We have one read-only copy for which is in the contiguous space for initialization, and when the system boots up, it will automatically create another copy, which is the default instance of the network stack. And we don't even see any difference in system behavior, but this default virtual network stack instance will be there. So it will be consuming slightly more kernel memory. And of course, there will be some performance penalty for accessing the virtualized variables because of the few levels of indirection that is needed for each access. But hold on. So in all days, basically, this was the overhead was not measurable. So we have more levels of indirection these days, but so this graph shows Lubeck throughput performance difference between a virtualized and non-virtualized stack. So it is definitely small, but can be observable on slower systems. But from the functional perspective, there's no reason why you couldn't have options vimage turned on by default and create jails just like you would do on a plain generic system, if that answers the question.
Sure it is, thank you.
Okay.
Another question?
Yeah, I have a question about the thing you said that you have in the future plans a feature that allows for two sockets for a socket being into virtual network stacks. I mean, do you plan to provide some sort of configuration to ensure security for this sort of solution? Yeah, like to make sure that there is no leakage of packet content between those zones.
So basically, this is so the leakage is really so if you had one socket open in one Vnet and another socket in another Vnet, those sockets are separate by definition. So if you have an application that would bridge between those two domains, basically that's
you need to forward the packet yourself.
Yeah, you would need to do something in your application, and I think that's an interesting space as soon as this virtualization concept will become more accepted. The demand for such applications would would certainly arise sooner or later. In fact, here is the issue only about the API, which would allow us to open sockets in different Vnets. Because now, once we switch to jail, which is subordinated in the jail hierarchy from us, we cannot go back. So we need to to come up with a API that would allow that. But from the security perspective, this wouldn't change anything. So we would just need a new API which would allow us to say, open a socket in that jail, but don't switch, don't spawn a new process in there. Keep it attached to the running process. Something like effective, like real user ID and effective user ID. Something I was thinking about that line, but just didn't have time to play more about that idea.
Other questions? If not, thank you very much.
Okay, thank you.